So students, now we'll be talking about plasma confinement using magnetic field. And as we understand that to attain a temperature of 10 to the power of 11 Kelvin, having something in that range, it's not possible to carry out that thing in any material because everything that's out there will be vaporized at that very temperature. So what is important here is that we should be in a position to confine this plasma. If we are able to confine this plasma without having actual connection with the shield, then that could be the possible way to have nuclear fusion. Uh, and and what is to be made sure here is that the plasma that we have, it should the ions of this plasma should not come in contact with the tube in which this plasma is generated. And at the same time, what we understand is that if we have charged particles in magnetic field, we have Lormer's precession, and certainly we can influence the motions of these charged particles using magnetic field. So in this case, what we do is that what we have is we use magnetic field on the charged particles, and these particles gyrate. They gyrate along the line of the force, and and the positive particles in one direction, and the negative particles in another direction. So for the sake of argument, so the positive particles will gyrate in one direction, and the negatively charged particles will gyrate in an opposite direction. So that's the part. Apart from the effect of collision, the ions and electrons, they remain tied to the field lines, these ions and electrons. So they can move parallel to the lines of force. And if a means can be found to prevent their escape, to prevent their escape at the end of the field lines. So there is a possibility of confining this plasma by means of magnetic field, static magnetic field. And to find the magnitude of such a field, let's write down the Maxwell's equations. So what we have divergence of D is 4 pi rho. Okay, this is my equation 1. Then I have the divergence of magnetic field, that is equal to 0. Okay, and then I have curl of electric field is minus 1 by C dou B by dou T. So this is over Faraday's law. And then we have Ampere's law, modified Ampere's law. That's curl of B is 1 by C times 4 pi J plus dou D by dou T. Okay. So these are the Maxwell's equations. Okay, so we have Gauss's law, we have Gauss's law in magnetostatics, and we have Faraday's law, and we have Ampere's law. So the point here is that the plasma that we have, it's assumed to consist of what? Electrons and ions, and they are free to move independently, so that the collisions are neglected here in this problem. And in the steady state, the force on all the particles per unit volume is just balanced by the rate of momentum transfer, by the rate of transfer of the momentum. And this rate of transfer of the momentum within the plasma, it's basically equal to what's called as it's equal to pressure gradient. So So what we have here is that we are assuming a steady state situation, and the force on all the particles per unit volume is just balanced by a rate of momentum transfer. And this momentum transfer that we have, this is basically this is this is equal to what's called as pressure gradient. So if I have to write down the force for ions, so force for ions, it's balanced by the pressure gradient, say delta pi. So for F, I will have Lorentz force, that is E plus 1 by C V ion cross B equals del pi. That should be the case. And for electrons, what we will have, F electrons should be equal to the pressure gradient. So here we will have E times E plus 1 by C V electron cross magnetic field is equal to del P electron. So that should be the case. Now, in a normal situation, what we have is the number of ions that are produced that must be equal to the number of electrons, and we can put them equal to n. So what we are going to get here if we add these two equations, so equation 1, no, this has to be equation 5 and equation 6. So let us add let's add 5 and 6. So so adding 5 and 6, what are we going to get? We are going to get n is common. Okay, then we have E by C, and what we'll get is VI and minus VE times B is equal to delta Pi plus delta P electron. And this should be the outcome of all this, right? And and what we have done is we have added the two equations, and on adding and keeping Ni equal to Ne equal to N, what we have is this. Now this will give me the total gradient in pressure. So I can write down here that this Ne by C is Vi minus Ve, B equals del P, where this del P is the pressure gradient due to the ions plus pressure gradient due to the electrons. Now, if we take on this Ne, this is simply NeVd, NeVi minus Ve. What is this? This is J. This is current density, and we can use J for this. And what will we get? We'll get 1 by C. I think I have missed the cross here, so it's cross. Sorry, cross. It's cross, and we understand that these are vector quantities. So let me go with the magnitude alone. Okay, so what are we getting here is 1 by C, and what we will have J cross B, and this must be equal to the overall pressure gradient that is developed in the plasma. Now, if we proceed from here, we can think of using this. What we have here is we have 1 by C. J cross B is del P. That's correct, absolutely. Now, if we go back to this equation where we have J, since we are talking about the static field, so this term will immediately be equal to 0. So what will be this J by C? That's going to be 1 by 4 pi del cross B. So here I'm using, instead of this term, I'm using 1 by 4 pi del cross B, and cross B is equal to del P. So this should be the output here. Okay, so now what we have is A cross B cross C, and everybody is aware about those vector formulae, and we can use down the one. So what we'll get is, maybe, did I do something wrong? No, it's okay. Yeah, J by C is, yes, it's 1 by 4 pi. Yeah. So what are we going to get here is, we have, let me write down this again, this is 1 by 4 pi del cross B, and then cross B is equal to the change in pressure, the pressure gradient, right? That's the case. Now we can use the formula here, and what we will have is 1 by 4 pi, this is minus del B square by 2, and then plus B dot del of B is equal to delta P. And this term is immediately equal to 0 because we are assuming field lines to be parallel. We are assuming that field lines are parallel. So this B dot del is immediately equal to 0. And what we are left with is, we are left with minus del B square by 8 pi is equal to del P. This is the case. Okay, this should be the case. So if I bring down it back, what I'll get minus del B square by 8 pi minus del P is equal to 0. Fine, nothing wrong with it. So I can have the equation here, I can have del outside. So inside I can have B square by 8 pi minus P is equal to 0. So what we can correlate this immediately is to what's called as, I can use this. What does it mean? It means B square by 8 pi minus P is simply a constant. And taking away the del operator that we have. Now, this constant certainly will have the dimensions same as that of the dimensions that we have on the left hand side of this equation. So we can choose a situation like this: 8 pi. This has to be plus. Okay, this is plus P. This is equal to B naught square by 8 pi. So what we have done is that what we have, this B square by 8 pi is the magnetic pressure. It's the pressure exerted by the magnetic field. Now, if the plasma is completely confined within an external magnetic field, if we have to confine it within an external magnetic field, so what's going to happen in that case is that this constant has to have a nature like this, but this B naught will be the external magnetic field that has to be applied. It's the external magnetic field that has to be applied in order to have confinement of plasma, so that the plasma does not touch the vessel, because if it touches the vessel, then everything is ruined. So if the magnetic field within the plasma vanishes, this is the magnetic field within the plasma, if it vanishes, what we are going to have? We are going to have this pressure equal to B naught square by 8 pi, and its value is 2n kpt. Now from this equation we can calculate this B naught square. That's our job, and let's go with it. So what we have is we have this B naught square by 8 pi is 2, and n is of the order of 10 to the power of 15 particles. It's the density of the particles, it's the density of ions and electrons. And Kb is the Boltzmann constant, it's 1.37 times 10 to the power of minus 16. And the temperature that we have, it's of the order of 10 to the power of 9 Kelvin. So from here we can calculate this, this B naught. This B naught nearly comes out to be equal to 10 to the power of 5 Gauss. And this magnetic field is a pretty ordinary magnetic field, and this magnetic field can be produced inside the laboratories. We can produce this much of magnetic field so that we can confine this plasma. And at the same time, now this magnetic field is not, it's not difficult to produce this much of magnetic field in the laboratory. So the confinement of the plasma by the static magnetic field is definitely possible. It is possible, at least theoretically. And the radius of gyration that this plasma should have, this radius of gyration should be smaller than the radius of the discharge tube. So if we have a discharge tube and if we have plasma, the radius of this plasma should be less than that of the tube that's enclosing this plasma. Otherwise, the particles will be lost due to the collision with the wall. They'll be gone. So for that, what we have is we can think of mv squared by r. This mv squared by r should be equal to BeV by C. So R can be calculated from here. That will be mv. That will be mvc by Be. And thinking about kinetic energy. So what's kinetic energy is 1/2 of mv squared equal to kBt. What we will have is we will have this velocity. This velocity will come out to be 2 kBt by m under root. And this R can be calculated. So V is here. We can substitute this V in this equation, and we can calculate R. And this R will it will certainly be C times 2mkBt whole raised power 1/2 divided by Be. So if we choose this kBt, if we choose it 100 kilo electron volts, and if we choose the magnetic field equal to 10 to the power of 5 Gauss, we come up with the radius. The radius of gyration comes out to be 0.01 centimeter. And for electron, this is for the electron, and for deuteron, this R will come up to be 0.60 centimeters. This will be for 0.60 centimeters for deuteron, and this radius will be 0.72 centimeters for tritium. Now, as the radius of the discharge tube is of the order of few centimeters, so it is evident that the radius of gyration is very less. So the tube that we have, it has a diameter of the order of few centimeters, say 3 to 4 to 5 centimeters. But we can see here that this radius of gyration for electrons, for deuterons, for tritium, it is not even 1 centimeter. So this means this radius is quite smaller than the tube radius, and the particles will not be lost. They will not be lost due to the collision with the walls. And certainly this method seems to be feasible, and the magnetic field of the order of 10 to the power of 5 Gauss will be able to confine the plasma. Okay.